This webcast continues in Worksheet 8F and works problems 5 and 6 in the section under Power. Okay, so these problems will calculate power, which is the rate at which work is done. So let's look at number 5. This is talking about the trains on a roller coaster called the Boss. And they start at a position of 10 meters. And it says that that's on the loading platform, but the roller coaster goes to a height of 60 meters at the top of the first hill. So we're going to take position A to be when they're on the loading platform, and position B to be when they're at the height at the top of the first hill. And it says to ignore friction. So the only type of energy that this problem is talking about changing is the gravitational energy. The train has a little bit of gravitational potential energy at position A, but it has much more gravitational potential energy at position B because it's much higher. And we're talking about the train and the Earth as our system. So where did this energy come from? There must have been work that transferred energy into the system of the train. And that work was done by the motor that's exerting a force on the train. I have gravitational energy on both sides of the equation, and so I want to be sure to use subscripts. So my conservation equation becomes that the gravitational potential energy at the beginning plus the work that was done on the train equals the gravitational potential energy at the end. Okay. And we're looking for the power of this motor, but in order to find the power, I have to find the work, because power equals work divided by time. Okay. So let's solve for the work here. The work is going to be the gravitational potential energy at the end minus the gravitational potential energy at the beginning. And so that's the mass times g times the final height minus the mass times g, the initial height. Let's see, the mass was 2,500 kilograms. G is 9.8. The final height was 60 meters. The initial height was 10 meters. And so I can solve for this here. And I get 1,225,000 joules. That is the work that was done on the train. The power equals the amount of work that was done divided by the time. Okay, so it's that 1,225,000 joules. That was done in 45 seconds. And so the power must have been 27,222 watts. Let's look at number 6, the next problem. Here we're talking about an elevator. It begins at rest on the ground. So there is really no mechanical energy of that elevator at the beginning. The system is the elevator and the Earth. But after 30 seconds, it's moving at 1.8 meters per second, and it's 4 meters high. So it has both kinetic energy because of its motion and gravitational potential energy because of its height at the end. That energy at position B had to come from somewhere. It wasn't in the system at the beginning. So there must have been a transfer of energy into the system by the work that the motor did on the elevator. That work equals the change in the kinetic energy plus the change in the gravitational energy. Okay, so let's take that energy conservation equation and figure out how much work was done. So the work would be 1/2 the mass of the elevator times its velocity squared plus the mass times g times the height. The mass is 900. It was moving at 1.8 meters per second squared at position B. And it's at a height of 4 meters. Okay, so I can solve for the work here. And I get that the work is 36,738 joules. But it's asking me for power, which is the work divided by the time. So I take that 36,738 joules, and I divide by the time, which the problem tells me was 30 seconds. And I get 1,224.6 watts.